Okay, in this lecture we're going to begin our Chapter 6 material on the Laplace transform. And in this first section, 6.1, we will start by defining the Laplace transform. Now, before we can get to the definition of the Laplace transform, we're going to introduce a little bit of background theory and terminology. So let's start with a definition of what it means for a function to be piecewise continuous. So here we say that a function f is piecewise continuous on an interval from a to b if that interval can be partitioned by a finite number of points. So let's say our t interval from a to b, we can partition by choosing several different t values, say t0 up through tn within that interval, so that our function f is continuous on each subinterval, tj to tj plus 1. And f has a finite limit as the endpoints of this interval are approached from within that interval. So let's take a look at some different types of continuity for a function. So we know what it means for a function to be continuous. We've seen both a formal definition of continuity in Calculus 1, and we know intuitively what it means for a function to be continuous over some t interval from a to b. It means that on this interval, our graph does not have any holes, jumps, or vertical asymptotes. Or we can think about drawing the graph of our function without picking up our pen. So here we have an example of the graph of a continuous function. For piecewise continuity, let's consider an example. Let's say on some interval from a to b, we have a function which might be not continuous, because let's say we have some jumps at particular values. However, let's say we can partition this interval from a to b into a finite number of subintervals by choosing partition points. Let's say t0 is our left endpoint a, t1 is the time where we had the first jump, t2, the value of t where we had the second jump discontinuity, and then t3 would be our right endpoint b. So we see that on each of these subintervals, t0 to t1, t1 to t2, and from t2 to t3, our function is continuous on those subintervals. And we don't have any infinite limits as we approach the endpoints of these subintervals. So this would be an example of a piecewise continuous function. And then lastly, as an example of a function which might not be continuous nor piecewise continuous on subinterval, well, we could have, let's say, on the interval from a to b, a function which has a vertical asymptote. So let's say we have a function whose graph looks something like the following. So we see it is certainly not continuous because we have both a jump discontinuity and a vertical asymptote at one point. And this is also not piecewise continuous because although I can partition this interval into a finite number of subintervals, I do not have a finite limit as my graph approaches t2 from the right-hand side. I see that my function is becoming increasingly large, giving me an infinite limit as I approach one of those endpoints. So here we have a function which is neither continuous nor piecewise continuous. So let's look at one example working with continuity or piecewise continuity before we start moving on to define our Laplace transform. In this first example, we are asked to sketch the graph of this function f of t, which is defined piecewise, and it's defined differently on 3 different subintervals, from t equals 0 to 1, 1 to 2, or 2 to 3. And then we want to determine whether that function is continuous, piecewise continuous, or neither. So let's start by sketching our graph here. In the ty plane, we're looking over the interval from 0 to 3. And on the first part of my domain, from time 0 to 1, f of t is defined as t. And the graph of f of t equals t is just a line with slope 1 passing through the origin. So at time 0, we have a y value of 0. And then when t is 1, we have a y value of 1. Now, as soon as t becomes greater than 1, on the interval from 1 up to 2 inclusive, f of t is defined as 3 minus t. So as t is approaching 1 from that right-hand side, the value of my function, 3 minus t, would be approaching 2. And then as t increases towards a value of t equals 2, 3 minus t will decrease with the slope of negative 1. And when we get to a value of t equals 2, our y value, 3 minus 2, would return to 1. So at time t equals 2, we return to a value of 1. And then for all t greater than 2 and less than or equal to 3, f of t is a constant, 1. So our graph would be a horizontal line passing through y equals 1 up until we hit time 3. So this is the graph of that function. And looking at the graph, we can see that it is not continuous because we have a jump discontinuity at time 1, but this is piecewise continuous on the interval from 0 to 3 because I could partition my interval into 2 subintervals, namely from 0 to 1 and from 1 to 3, and we have continuity on each of those subintervals and no infinite limits. So here we could state that this function is piecewise continuous. Now, before we define our Laplace transform of a function, let's introduce a little more terminology the bottom of our page, let's define the following. We would say a function f is of exponential order if the magnitude or absolute value of f of t is less than or equal to k times e to the at for values of t greater than or equal to m, where k, a, and m are real constants. So this definition, what does it mean? Well, we say a function is of exponential order if this function grows not as rapidly as an exponential of the form k e to the at for sufficiently large t. So again, we do not have more rapid growth than an exponential growth. And that's what it would mean to be of exponential order. Now, most of the functions that we work with are of exponential order, but what would be some functions which are not of exponential order? So we could consider functions like maybe e to the t squared, because here our exponent of that function is quadratic, so it would grow more rapidly than any function of the form e to the a times t, that is e to a linear power. Or even worse, we might consider something like e to the t power, which certainly grows more rapidly than e to the at power. So now that we have introduced some terminology, we are ready to define our Laplace transform and talk about its existence. So let's consider this definition. Suppose we have a function f of t, which is defined for all t greater than or equal to 0. Then we would define the Laplace transform of that function as follows. So let's start with notation. So the notation that we're going to use for the Laplace transform is a cursive L, and then in braces, the function f of t that we're taking the transform of. And it's defined in terms of an improper integral. We have the integral from 0 to infinity of e to the negative st times the function that we're taking the transform of, f of t, integrating with respect to t. So here we're evaluating a definite integral in terms of the variable t. So when we evaluate this integral, since it's a definite integral in terms of the variable t, t disappears, and I'm left with a function that involves this new variable that I introduced, s, in that exponent. And so another notation that we can use for the Laplace transform of a function, little f of t, we could use the notation capital F of s. So we use the same variable, but capitalized for the Laplace transform of a function denoted by that lowercase variable. And so what we get for the Laplace transform of a function is a new function, which depends on this new variable we've introduced, s. And the Laplace transform is defined in this way, provided that this improper integral converges. So we need to make sure that we have convergence of that improper integral for the Laplace transform of a function to be defined. So before we look at some examples of calculating Laplace transforms, an important question might be, when we guaranteed that the Laplace transform of a function will exist. How do I know that that improper integral will converge? And the answer to that question is given by the following theorem. This is theorem 6.1.2 from your text on the existence of the Laplace transform. And so here's what it says. Suppose that we have a function f which is piecewise continuous on the interval 0 to a for any a. So essentially it's piecewise continuous on the interval 0 to infinity, since a can be any value, and of exponential order. So the function does not grow more rapidly than an exponential of the form e to the at for large t. Then we are guaranteed the Laplace transform of that function exists for particular values of s greater than a, where a is the constant that we had for this exponential bound on our function. So as long as we have relatively nice functions, that is piecewise continuous and of exponential order, the Laplace transform of that function will exist at least for some values of s. So finally, now that we have defined the Laplace transform and talked a little bit about its existence, let's look at some examples of finding the Laplace transform of a function. So the first one that we have here in part A is the function f of t equals 1, a constant function. And so let's look at our Laplace transform of this. The Laplace transform of 1. So by definition, the Laplace transform is given by the integral from 0 to infinity of e to the negative st times the function that we were taking the transform of, so in this case times 1 dt. And to evaluate an improper integral over an infinite interval, say from 0 to infinity, we need to make use of limits. So we could take here the limit of the integral from 0 to some variable, let's maybe use n, as n approaches infinity, of this e to the negative st dt. So this gives us the limit as n approaches infinity of, for the antiderivative of e to the negative st with respect to t, we have negative 1 over s e to the negative st from 0 to n. And so this gives us the limit as n approaches infinity of negative 1 over s e to the negative sn minus negative 1 over s e to the 0. So that leaves us with a plus 1 over s. And now taking our limit as n approaches infinity, well, the only term that involves n is this first term, e to the negative sn. And so as n becomes infinitely large, this term will decay to 0 as long as the value of s in that exponent is positive, so that we have e raised to larger negative numbers as n increases. And so we would have 0 plus 1 over s, and again, this was guaranteed as long as s was positive in order for that exponent or that exponential function to decay to 0. Okay, so we have here our Laplace transform of the constant function 1. Now let's take a look at part B. In part B, we have the function f of t is a general exponential, e to the at. So let's take a look at finding our Laplace transform of this function. By definition, it is the integral from 0 to infinity of e to the negative st times the function I'm taking the transform of, which is e to the at, integrating with respect to t. And so here, if I combine those exponential functions in my integrand by using properties of exponents, I get e raised to the sum of those terms, negative st plus at, which I could rewrite as negative of s minus a times t dt. And again, to evaluate this improper integral, I need to make use of limits. So I would take the limit as n approaches infinity of the integral from 0 to n of e raised to the negative s minus a t dt. And so I have the limit as n approaches infinity of, for my antiderivative, I get negative 1 over s minus a e to the negative s minus a times t, evaluating from 0 to n. So we have the limit as n approaches infinity of negative 1 over s minus a e raised to the negative s minus a times n minus a negative 1 over s minus a e to the 0. So that leaves me a positive 1 over s minus a. And now taking our limit as n approaches infinity, again, the only term involving n is this exponential term. And this term will decay to 0 as n becomes large, as long as this expression in front of n, s minus a, is positive. So that as n becomes larger, we have exponential decay. In which case I'm left with 0 plus 1 over s minus a. And again, this was true as long as s minus a is positive, or equivalently if s is greater than a. Okay. So we have established here the Laplace transform of the constant function 1, along with an exponential function, e to the at. So let's look at some other examples. In this next one, we are asked to find the Laplace transform of the sine function. F of t is sine of at. So again, to find the Laplace transform of a function, in this case sine of at, we take the improper integral from 0 to infinity of e to the negative st times the function that we're taking the transform of, which is sine of at, integrating with respect to t. And to evaluate this, we have to make use of a limit. We would take the limit as n approaches infinity of the integral from 0 to n of e to the negative st sine of at dt. So we need to find an antiderivative of e to the negative st sine of at. And to do this, we're going to make use of integration by parts. You might recall from Calculus 2 that this is an integral that requires integration by parts twice, and we get back the same integral that we started with, sometimes called the loop integral. So let's look at evaluating this. Using integration by parts, I need to choose part of my integrand as u, and the rest of it as dv. So here I could choose u as my exponential function, let's say e to the negative st, in which case dv would be sine of at dt. And so du would be negative s e to the negative st dt, and v would be negative 1 over a cosine of at. So using the integration by parts formula, we find that the antiderivative of e to the negative st sine at is given by u times v, so a negative 1 over a e to the negative st cosine at minus the integral of v times du. And for v times du, I have s over a e to the negative st cosine of at dt. So the integral that I'm left with after I apply integration by parts is of a similar form to the integral I started with. We have an exponential, e to the negative st, but now times a cosine function. So to evaluate this integral, let's again apply integration by parts. So we need to choose u and dv. And I'm going to choose them in the same way that I did for my first application of integration by parts. U is going to be my exponential function. So here I had a constant s over a e to the negative st. And then dv will be my trig function, cosine of at dt. In which case du is negative s squared over a e to the negative st dt, and v is 1 over a sine of at. So taking what we had from above, we now have the antiderivative of e to the negative st sine at dt is equal to, well, we had a negative 1 over a e to the negative st cosine of at, and then we were subtracting, applying integration by parts to that second integral. We have u times v, which would give us s over a squared e to the negative st sine at, minus the integral of v times du. And for v times du, we have a negative s squared over a squared. So subtracting this, I get a plus s squared over a squared. integral of e to the negative st sine at dt. And so what I have now is an algebraic expression involving this unknown integral. We see that after the second application of integration by parts, I end up with the same integral that I started with, e to the negative st sine of at, but being multiplied out in front by a negative s squared over a squared. So if I treat this integral as a variable, I could move everything involving that variable to the left-hand side of my equation, and I have 1 times that integral plus s squared over a squared times that same integral, leaving me with s squared plus a squared over a squared times this integral. And on the right-hand side, I have a negative 1 over a e to the negative st cosine at minus s over a squared e to the negative st sine at. So solving for this antiderivative, I would multiply both sides by a squared over s squared plus a squared, leaving me with negative a over s squared plus a squared e to the negative st cosine at minus s over s squared plus a squared e to the negative st sine of at. So let's take a look back at this improper integral we're evaluating. Using what we just found for this antiderivative, we're going to be looking for the limit as n approaches infinity of this antiderivative evaluated from 0 to n. So when we substitute n in place of t, we have a negative a over s squared plus a squared e to the negative sn cosine of an minus s over s squared plus a squared e to the negative sn sine of an. And then we subtract what we get by substituting 0 in for t, which would give me a negative a over s squared plus a squared times 1. And since I was subtracting that negative, we get a plus a over s squared plus a squared. So finally, taking my limit as n approaches infinity, well, I have these terms that involve an exponential times a sine or cosine. And so as long as s, the coefficient in this exponent, is positive, those two terms will decay to 0 with oscillations from the sine cosine terms. And I'm left with altogether 0 plus a over s squared plus a squared, again provided that s is positive. So here we have found the Laplace transform of this sine of at function, where a is some arbitrary constant. And so let's look at some other examples. In this next one, we are asked to find the Laplace transform of this piecewise defined function, f of t, which is equal to t on the interval from 0 to 1, and 0 for all t greater than or equal to 1. So let's take a look at how to find the Laplace transform of a piecewise defined function. For the Laplace transform of this f of t function, we know we are taking the integral from 0 to infinity of e to the negative st times the function I'm taking the transform of, f of t, with respect to t. And here, f of t is defined differently depending on what t interval we're working on. So to evaluate an integral of a piecewise defined function, we would split up our integral into the sum of definite integrals over each part of the domain of this function. So starting with the interval from t equals 0 to 1, we have e to the negative st times f of t, which is defined as t on the interval from 0 to 1. So we get t times e to the negative st. And then we are adding the integral from 1 to infinity of e to the negative st times, on that interval, our function is defined as 0. So for the second piece of this Laplace transform, we're integrating 0. So we are left with a value of 0 there. And now we are just evaluating the integral of t e to the negative st from 0 to 1. So to evaluate this, we're going to make use of integration by parts. So I need to choose a u and dv. Here I would choose u as t, in which case dv is e to the negative st dt. And so du would be 1 dt, and v negative 1 over s e to the negative st. So we now have this integral from 0 to 1 of t e to the negative st dt is given by u times v. So we have a negative 1 over s, t e to the negative st. We're evaluating from 0 to 1, minus the integral from 0 to 1 of v du. So I'm going to get a negative 1 over s. So subtracting this becomes plus 1 over s, the integral of e to the negative st dt. And so I have, evaluating this second integral, a negative 1 over s squared e to the negative st. And we're evaluating this antiderivative from 0 to 1. So substituting 1 in for t, I get negative 1 over s e to the negative s minus 1 over s squared e to the negative s. And then I subtract what I get by substituting in 0 for t, which would be a negative 1 over s squared. Since I'm subtracting that, it becomes plus 1 over s squared. So this would be the Laplace transform of this piecewise defined function. And of course, this could be generalized to evaluate the Laplace transform of a piecewise defined function. We could split up our integral from 0 to infinity into an integral over different subintervals and evaluate each piece. So let's take a look now at one important property of the Laplace transform, namely that it is a linear transform. So we have the following theorem, which is known as linearity of the Laplace transform. And here's what it says. Suppose that we have two functions, f1 and f2, whose Laplace transforms exist. Then the Laplace transform of a linear combination of f1 and f2, something of the form c1 f1 plus c2 f2, is equal to a linear combination of the Laplace transforms of those functions. That is c1 times the Laplace transform of the first function plus c2 times the Laplace transform of the second function, where c1 and c2 are constants. So this theorem says, well, just like for limits, derivatives, or antiderivatives, we can take a Laplace transform of a linear combination of functions term by term. So let's prove this result. Here, we're looking for the Laplace transform of a linear combination of two functions, f1 and f2. And by definition, this is the integral from 0 to infinity of e to the negative st times the function I'm taking the transform of, which is c1 times f1 plus c2 times f2. So if I distribute my exponential term within this integral, I have c1 e to the negative st f1 plus c2 e to the negative st f2. And then because an integral is a linear operation, I can take my integral term by term, giving me the constant c1 times the integral from 0 to infinity of e to the negative st f1 plus c2 times the integral from 0 to infinity of e to the negative st f2. But this is exactly c1 times the Laplace transform of the function f1 plus c2 times this improper integral, which is the definition of the Laplace transform of f2. And this is what we wanted to establish. So making use of this linearity property, let's look at one last example. Here we are asked to find the Laplace transform of the function f of t, which is 6 plus 2 e to the 3t plus 4 sine of 5t. So let's take a look at this. We're looking for the transform of 6 plus 2e to the 3t plus 4 sine of 5t. And so by this linearity property of the Laplace transform, well, I could think about this as taking the Laplace transform of 6 plus the Laplace transform of 2e to the 3t plus the Laplace transform of 4 sine of 5t, or by bringing these constants out in front of these transform operations, this is the same as 6 times the Laplace transform of 1 plus 2 times the Laplace transform of e to the 3t plus 4 times the Laplace transform of sine 5t. And so what I'm left with, these three expressions, the Laplace transform of 1, e to the 3t, or sine 5t, well, those were the functions that I found the Laplace transforms of in my previous examples from this section. So let's take a look at it here. We have 6 times the Laplace transform of 1, which we found to be 1 over s if s is greater than 0, then plus 2 times the Laplace transform of e to the 3t. Well, we saw the Laplace transform of e to the at is 1 over s minus a. So in this case, a is just 3. As long as s is greater than a, so as long as s is greater than 3 here, plus 4 times the Laplace transform of sine 5t, and we saw that the Laplace transform of sine at is given by a, so in this case 5, over s squared plus a squared, so s squared plus 25, if s was positive. So simplifying just a bit, we have 6 over s plus 2 over s minus 3 plus 4 times 5, or 20, over s squared plus 25. And let's think about what the condition on s is for this transform to be defined. We needed s to be greater than 0 and also greater than 3. So to make sure all three of these conditions hold, we need s to be greater than 3. Because certainly if s is greater than 3, it is automatically greater than 0.